Hello everyone, I am Jeffrey, and my teammates are Scott, Garrett, Jillian, and Corbin. Today we'll be tackling SMB. Now, what is SMB? SMB, or Server Message Block, is a network communication protocol used for file sharing, printer access, and network browsing. It also allows applications and users to read, write, and request services from servers in a networked environment. While SMB is most commonly associated with Windows systems, it's also supported on Linux and Mac OS through third-party implementations like Samba. Essentially, SMB makes resource sharing seamless across the network, which allows users to access remote files and services as if they were local. Now, how does SMB work? SMB operates on a client-server model, meaning that a client device like a workstation requests access to shared resources hosted by a server. SMB primarily runs over TCP port 445, which allows direct communication over IP networks without the need for older NetBIOS protocols. Another important feature of SMB is inter-process communication, or IPC, which enables different processes to exchange data using named pipes. Now, over the years, SMB has evolved through multiple versions to improve security and subsequently efficiency. SMB v1, introduced by IBM in the 1980s, relied on NetBIOS and had limited security features, while SMB v2, released in 2006, reduced the number of commands, thus improving efficiency and security. Now, SMB v3, introduced in 2012, added significant security upgrades, including encryption using AES and pre-authentication integrity checks to protect against attacks such as man-in-the-middle. These updates have made modern SMB versions much more secure, but vulnerabilities still exist, especially in older versions.
Alright, now that we know what SMB protocol is, let's dive into its vulnerabilities. To start, SMB is everywhere. From file sharing, printer sharing, remote services, and more, it has very broad applications. Even though each version introduced security improvements, inherent weaknesses remain. I'll be covering general vulnerabilities, and Scott and Corbin will dive deeper onto attacks that exploit them. So first, legacy code. Older versions like SMB version 1 are still enabled on many machines. And the more capabilities, the more attack vectors there are. SMB is designed to enable communication, which is exactly what's attractive to abuse, especially when looking to traverse a network. When we have a protocol that is made for network browsing or discovering devices, connecting users, communicating with devices, pipes, or files, get control of SMB in the network, then you get a ton of power. Let's break this down by looking at some major versions, starting with SMB version 1. There is no encryption, so credentials are sent in clear text with NTLAN Manager version 1 hashes, making them very easy to intercept, as in during the authentication stage. NTLM, by the way, is a legacy challenge response authentication protocol used by SMB for verifying users and their credentials. They're known to be vulnerable because they don't use strong authentication by default. Also, the way SMB transmits or relays the hashes is prone to interception in relay attacks and used to impersonate users. SMB version 1 also has buffer overflows, so static memory allocation, like the SMB com transaction function, allows exploits to send oversized requests to overflow into kernel memory, leading to remote code execution. This is what Eternal Blue abuses. Then there is null sessions, so sensitive IPC shares would have no authentication during the discovery phase, for example, which is like walking into a bank with no ID. Next we have SMB version 2. Even though it's much faster and introduced HMAC SHA-256 for message signing, there's still issues. It has command parsing flaws, so malformed headers like SMB2 compound request is abused to bypass validation or trick systems into executing remote code execution. Then we have session hijacking. Missing mutex locks in the SRv2 system driver file during session handling allows ability to spoof message ID values to crash systems or open backdoors. Next we have SMB version 3 and SMB version 3.1.1. They did make security improvements, but still has flaws, and the culprit is compression. There's a math error in the decompression function, SRv2 decompress data, introduced in version 3.1.1. It was proven to allow sending malformed packets to trigger integer underflows and overflows to corrupt kernel memory. We see this exploited by SMB Ghost, which we'll delve in deeper, and later on SMB adapts this even more. Another thing is encryption gaps. Pre-Windows 10 systems using SMB version 3 could disable AES-CCM encryption. This was done by manipulating the SMB2 global cap encryption flag, resulting in interception of data in transit. Beyond version-specific stuff, let me just mention SMB's vulnerability takeaway. We have IPC shares, so misconfigured named pipes, allows ability to steal credentials via Mimikatz during service interaction. And NTLM authentication. So during authentication, SMB relies on reusable hashes, which can be intercepted, spoofing, which are relayed to hijack sessions. So if NTLM is enabled, even in later versions, that backwards compatibility would have issues. And misconfigured shares, so publicly exposed files is a ransomware favorite, so if there's misconfiguring there, then that's an open fault. Memory mismanagement. We're seeing a common theme is poor handling of requests and buffer allocation, leading to crashes or code injection or overflow-focused attacks. So the overall pattern is that attackers exploit SMB's trusted role in networks. And here's some major attacks fueled by SMB's weaknesses. We have WannaCry, used Eternal Blue to spread ransomware via the SMB version 1 buffer overflows. We have NotPetya, weaponized Eternal Blue for lateral movement, causing over 10 billion in damages to Ukrainian infrastructure. Then we have Emotet, use SMB version 1 credential relays to deploy banking Trojans. And then we have Phobos ransomware in 2023, leverage SMB version 3.1.1's compression flaws to bypass network segmentation. And
This is Scott Anderson, and I'll be walking you through the Eternal Blue exploit and understanding it and how it works. First, as an introduction, it was developed by the NSA, and it was made public in 2017 when the Shadow Brokers released a whole bunch of different NSA hacking tools. It mainly targets the SMB version 1 protocol, specifically CV 2017-0144, and it allows for remote code execution through a buffer overflow. So how it works, it exploits 3 distinct SMB version 1 flaws. It uses a specially crafted SMB packet to achieve this, and it leads to buffer overflow and arbitrary code execution. So the first bug that it takes advantage of is an integer overflow. This occurs when the SMB protocol converts from a OS2 file extended attribute structure to an NT file extended attribute structure. During this conversion, a miscalculation occurs, causing an integer overflow, which in turn causes less or allows less memory to get allocated than needed. And with this smaller allocation, a buffer overflow can occur. The second bug, which is the buffer overflow itself, involves 2 SMB commands. First one is the SMB com transaction 2, and then the second one is the SMB com nt transact. The nt transact requests a packet twice the size of the transaction 2 command, and when this happens, the SMB assigns memory based on the last packet received. So if you send the NT transact immediately before the transaction 2, this will cause SMB to allocate the size based on the smaller packet, and that will result in inefficient memory allocation, triggering the buffer overflow. The third bug that Eternal Blue takes advantage of is heap spraying. Attackers can use heap spraying to allocate a chunk of memory in a specific location. Malicious code is then placed into those memory locations, and once those locations are triggered or directed to, it will cause the malicious code to run, and thus gaining a foothold into the system. So to exploit Eternal Blue, it is fairly simple. You can use Nmap to scan the target system, and more specifically, you'll use the Eternal Blue Nmap scripting engine script, as you see there, the SMB Vuln MS17-010. That will scan specifically for Eternal Blue vulnerable machines. Once you've found that a machine is vulnerable to Eternal Blue, you can use Metasploit, and you can use the MS17-010 module, which is Eternal Blue. Using that module, you would just set the required parameters, and then you run the exploit, and you have now exploited Eternal Blue. Once you have exploited it, things to do after that is to try to get privilege escalation of getting system privileges. You can extract credentials that are on the system and send them off to your command and control center and try to crack the hashes of those credentials. And then you can also set up persistence, whether that be a backdoor to gain or to continue access, or if you are running any other types of malware, whether that be ransomware or viruses of that sort.
Hello, my name is Corbin. I'm going to be going over attack methodology number 2, SMB Ghost. So SMB Ghost is a critical flaw in SMB version 3. It's rooted in the issue that SMB version 3.1.1 handles compressed data packets in a weird way. So obviously this was introduced with SMB 3 to optimize network bandwidth, but it backfired. Basically, there's a logic error that leads to mishandling of compressed data. So in order for this attack to work, you have to be running SMB version 3, and compression must be enabled. And then in the context of the exploit, any systems with an open 445 port exposed to internet are highly vulnerable. So attackers, when they scan and see that this is open, are very likely to know what to exploit. So how does it work? Basically, improper bounds checking during the decompression leads to integer overflow, and then this can lead to a buffer overflow in adjacent memory, and also corrupt memory. Okay, so what does this actually accomplish? So there's two things we can do with this. Remote code execution is the ideal condition. Again, by sending these malicious packets, we can basically execute our own arbitrary code without needing any authentication to do so. And then if done wrong, it can just lead to a denial of service, which can also be useful. Okay, so here's a code example. So the problem really starts on line 20 and line 31. So you can see on line 20 here that you have the original compressed segment size and then the offset. And so this is where, when you send a malformed packet, you can basically create an overflow. Okay, so let's talk about like some more advanced techniques and how this is actually used. So SMB Ghost is very wormable. This means it can just propagate across networks with very little user intervention. Very similar. It's very similar to WannaCry and NotPetya, and that's all I have.
All right, so now that we've learned about a couple of attacks, I'm going to be going into the impacts and mitigations of the SMB attacks. So SMB attacks are aimed at the SMB protocol, so if attacks are successful, it can be devastating because the SMB protocol is highly ingrained into most workstations nowadays. Two large attacks that we covered in this presentation are Eternal Blue and SMB Ghost. Each of these exploits use the SMB protocol to infect a host. After connection, you can do a multitude of operations on the host, from installing ransomware to remote code execution. We can defend against these attacks with a multitude of preventative measures to prevent and detect these types of attacks. Moving on, impacts related to Eternal Blue and SMB Ghost. Eternal Blue has been used in many attacks, but one of the largest by scale was the WannaCry attack on May 12, 2017. This attack was a worm that infected over 200,000 computers and installed ransomware that disabled access if the user did not pay the fine. It was shut down within a couple hours, but this really shows you how effective the attack was. By using the SMB protocol to infect and install this on the hosts, within a couple hours it was able to infect that amount of computers in over 15 different countries all across the world. SMB Ghost, on the other hand, is exploited within the compressed data packets of SMB v3. So within the exploit, you can do many things on the host, including remote code execution and denial of service attacks. This can also be implemented into a worm-style attack like the WannaCry incident, and that would be awful because we don't need another one of those attacks. Going on to mitigation techniques, there are many mitigation techniques that you can implement to protect you from these attacks, including enforcing SMB signing, where when you enforce SMB signing before the connection, it requires both the client and the server to have a proper digital certificate so it can be tracked and traced back to whoever connected at this amount of time. Another way is enabling multi-factor authentication. We can also go into network segmenting and network monitoring, where both of these are kind of, if they do gain access to one of these, with the segmenting, they'll only have access to a certain portion of our network, while if you monitor, you can see their actions and what they did on your system. And there's also a bunch of other ones, such as firewall rules and many other techniques that you can do to prevent SMB as well. And thank you for tuning in. That is our presentation.